Thank you. Thank you very much for inviting me to this very interesting meeting and giving me the honor of opening it with my talk. It has many things in it. So it's curved space-time, quantum field theory, renormalisation group. So yeah, I guess maybe it works to kick things off a bit. I don't know if the proposal is still new because the paper is like, I don't know, maybe 2 years already. So, but I'm talking to you about it for the first time. So that's why it's new. Okay, so the idea here was to combine two things that are used in perturbative and non-perturbative quantum field theory. And one of them was algebraic quantum field theory, okay? And here, let me add perturbative because this is, primarily the setting I'm going to talk about. However, the hope is that in the future, this can lead to some non-perturbative results. Okay, so that's in brackets. So that's one setting. And the other, there are very powerful techniques used in renormalisation group, in particular, functional renormalisation group, or G. So these were kind of thought as two very different worlds, partially because the later one usually happens in Euclidean. Okay, so this is Euclidean signature, so you have to Wick rotate, and obviously if you're on curved spacetimes, this is not always possible. This is typically impossible, so of course it's somewhat awkward. But of course you can stay in Euclidean. Here, this setting is intrinsically Lorentzian. Okay, so the first kind of conundrum was, well, you know, how do I make these talk to each other? And the path we chose was to bring this over to the Lorentzian side. So we did something like that and made the connection. So this is the work, joint work with Edoardo D'Angelo, Nicolo Drago, and Nicola Pinamonti. So I will start with introducing a few concepts from perturbative algebraic quantum field theory, and anybody giving a talk on this will have their life easier now, and then talk a bit about FRG, and finally, formulate those flow equations that I promise. Okay, so part one. Also, just to make sure, I have 50 minutes plus questions. Okay, good. It's good to ask it before you start talking. So, perturbative algebraic quantum field theory. Okay, so this is a framework for constructing QFT models on curved spacetimes. So let's take a curved spacetime. So mg, globally hyperbolic. Okay, and I'm going to talk about scalar fields. So here, fields live in a space of smooth functions on M, valued in R. So this is scalar field. Or I should add real scalar field. So an element here will be denoted by chi. It's usually phi, but here we need phi for something else. Okay, and then observables, classical observables, can be understood as some functionals of fields. So classical observables. So these are functionals of fields. Okay, and I'm going to assume them to be smooth because I want to differentiate them a lot. So I'm going to be smooth functions. Let me give this some name. So let's denote this space by E. So smooth functions on E valued in C. Okay, and by the definition of smoothness, I'm using the derivatives here. So these are going to be Frechet derivatives. And, well, at each order, nth derivative at every point will give you a distribution on M. So here, if I have F, then Fn at point phi, so it's a distribution, so it's in the dual of the space of smooth functions on Mn. So n is the same here. This is a topological dual. And okay, so here I'm not giving the support restriction, hence these are compactly supported distributions. So compactly supported distributions. Okay, and knowing that, I can now talk about some refinement of what kind of functionals, what kind of observables I want to look at by specifying wavefront set conditions for these distributions. I'm going to assume that everybody knows everything unless there are questions. So please interrupt me if there is something you don't know, because I assume, well, in a sense, this conference is an intersection. Well, yeah, is it a sum or an intersection? If it were an intersection, then you probably know everything. But if this is the sum of all these topics, then there might be questions. So if there are some words that sound unfamiliar, then please ask. So are there any questions up to now? Okay, good. Just to make it clear. So yeah, so there is a distinguished space here that people work with in perturbative AQFT. So this is a space of microcausal functionals. Okay, and they are defined by the property that the wavefront set of that object Fn, maybe I should, no, I'm not Alex, I need this stick. The chair should pull down the board for me. I will use chi here. I should be using chi, consequently. Now I lost it forever. So this is supposed to be such that the intersection of this with the sum of, so this is the closed forward light cone, and this is the closed backward light cone. Okay, so that doesn't intersect that set. Okay, so this is motivated by properties of the two-point function of a Hadamard state. So I will get to that later. What else do we have? Okay, so this is the main space I'm going to work on, but there's a smaller space of functionals that come up commonly in physics, in particle physics. So there is the space of local functionals. So, yeah. Oh, yes, sorry. Yes. Thank you. Yeah. Good. So these are of the form so f of chi. So these are going to be given by integration of some smooth function of the kth jet of chi. Okay, and this is d mu x. So this is finite jet. So the value of chi and its derivatives up to order k, and this function is smooth. Okay, so examples, obvious examples. Like say, phi to the fourth interaction. So let's add it some coefficient, chi to the fourth. We need some sort of compactly supported thing here, because chi is not compactly supported. This is an integral over non-compact manifold. So let's smear it with a test function, and then we're good. So f has to be a test function, so smooth and compactly supported. Okay, so this is a primary example, and this leads me to the next topic here. So how to introduce the dynamics in my theory. So this uses Lagrangians, or, well, more precisely, generalized Lagrangians. As you have seen from this example, maybe, it's not really possible to realize, well, an action as an integral of the Lagrangian density itself because of compact support issues, but we are going to get close to that. So we are going to think about Lagrangians as Lagrangian densities with a cutoff. So here, a generalized Lagrangian okay, L is going to be a map from D, so the space of test functions, to local functionals, okay? And here, well, that would be an example. Another example is the Lagrangian of the free scalar field, which is going to feature a lot. So this maps F to L of F. And, oh, just I should say, this assignment should, in some sense, be local. So this L depends locally on F. So local map. Okay, not necessarily linear, but local. Here is linear, but it could be something else. And another example is the free scalar field Lagrangian. All right, so I call it I0 of F with configuration chi. Okay, so this is 1/2. This is the kinetic term. The covariant derivatives here. There could be some non-minimal coupling to the curvature. And there's, in principle, also a mass term here. And let's not forget the test function. And here I'm integrating with the canonical measure induced by the metric, because I have it. All right, so now with this, there is a way to extract the information about the dynamics, so I can, in some sense, compute the variation of this Lagrangian, and from this I get equations of motion. So variation gives equations of motion, and here in this example, well, this is not surprising. So here it's P0 on chi equals 0, where P0 is our old friend, the Klein-Gordon operator, word minus that. Okay, so we have the setup more or less, and then I have to review some facts which are probably known to people, but it doesn't hurt to hear it again. Yes? Yes. Oh, yeah. Well, this is very simple, this one, actually, because for this example, for local functionals, the first derivative is smooth, so that's clear. And the higher derivatives, well, I mean, the higher derivatives are going to be essentially some combinations of powers of deltas. Yeah, but for the local functionals, I mean, for the local functionals, you always get, I mean, yeah, there is more macrocausal functionals than local functionals. You always get this different. Yeah. Homework. I don't think it's different from the usual one. Maybe, Claudia, is it the same one you guys are using? Yeah, okay, good. I mean, just, you know, it's very possible that there are as many conventions as there are people in this community, but that's about the metric. No. No. Okay, easy. So before we get to the violent argument, so this talk is completely conventions neutral. So please insert your own conventions for what you think these symbols mean, and there is these are correct up to Z2. Okay, so this is going to be a lot of controversy now. So I'm now going to talk about retarded and advanced green functions, and there is also a bit of ambiguity which one is which. Okay, so for such guys, there exist unique retarded advanced green functions. Okay, retarded advanced such that, okay, so I'm using the convention that the support of delta retarded of f is to the future, and the support of delta advanced of f is to the past. And if you don't like it, you can flip these in your head. And I define the following object. So their difference is called the Pauli-Jordan function, or causal propagator. Pauli-Jordan function. Okay, and finally, from this, I can talk about the two-point function. So, I mean, for now, well, you may or may not think about the physics sort of language. So these are some green functions. So this guy is obviously a solution to P0. It's even a bisolution. So now here is the problem. So I want, well, this fellow doesn't satisfy, well, if you take the powers of that, that doesn't really match nicely with my wavefront set condition here. So this wavefront set condition is kind of motivated by what things can be nicely multiplied with the Weidmann two-point function in the vacuum, okay? So now I want to, on curved spacetime, I want to ask myself, does there exist something which, as far as singularity goes, behaves like two-point function, Weidmann two-point function in the vacuum? And this is exactly what Hadamard states do for you. So I need to find something I call delta plus, which has this guy as the anti-symmetric part, plus it has a symmetric part to go with it as well. So this is symmetric, and this is also a bisolution for P0. Okay, and what do I want from it? As I said, there's the wavefront set condition. So such that the wavefront set of delta plus, and here, okay, somebody has to call it, so I'm the first person, so I have to write it. So here, This is a subset of the cotangent bundle without the zero section. 2. This dot means without the zero section. And so the elements here are going to be pairs x, k, x, and y minus k, y, such that these guys are related. And, oh, this, actually I need slightly more space, but let me spell out this relation first. So this relation means that there exists null geodesic, and these vectors are cotangent to it. And kx minus ky are cotangent. Okay, so that's sort of generalization of just sitting on the light cone. And there is one more condition, sort of positivity condition. So, yeah, the first one, yeah. So kx is greater than 0. Sorry, that they are the race indices. They're yeah. Yeah. Sorry, I did. Yeah, sorry. Okay, yeah, they're co-parallel, so to say. All right, so that's the condition, and you can, well, check that this plays nicely with these derivatives. So if you take the powers of delta plus, then you can multiply them with these derivatives without harm. So that's the whole point of that story. Okay, so there's also one more. This delta plus should be positive definite. So let's add it here, positive definite as a distribution, because we want to think about it as a two-point function of a state. States are positive. Positive, yes. Sorry. Semi-definite. Yeah, this could be degenerate as well. Okay, so I need that to define a certain product on this space of functionals of interest. So define product, so F, and okay, so I'm going to label it by this choice of delta S, star G. This is defined as multiplication times, so here I denote here a differential operator where I take derivatives. Okay, I want to know how to take derivatives with respect to chi. I take derivatives of F and G a number of times, and then contract it each time with delta plus. And because of the wavefront set condition, this is well defined for Fg in microcausal. Okay, so that's done. Now you can ask, well, is there a unique choice of delta S? Is there some particular reason to choose one over the other? Well, on Minkowski spacetime there is. There's an extra condition of this whole thing being translation invariant that defines the vacuum. In general, there is no unique choice. So different choices of delta S. Well, in principle, you could be in trouble, but you are not, because it turns out that the products are equivalent. So different choices of delta S lead to equivalent products. Okay, so there is a map. Yes? Okay, I guess, so if we were talking about polynomials, then we don't have to do that, but okay. So let's put it here for now. And this is a caveat, not needed for polynomial fg. So typically you actually work with polynomials. So typically you don't have to do it at this stage. But yeah, if you want to treat more general things and you're not sure about the convergence, then yeah, we can stick it in for safety. Okay, so and then if we are doing it with h bar, and let's go ahead. So we can have two different products. We can also, well, we also have an involution. This is simply complex conjugation of functionals. So there is a map, which I call alpha, going from, well, so it was a different choice, the old choice. Okay. This is a different product, the same involution. And this map here, it's also of the exponential sort. So alpha ds prime minus ds is exponential h bar half, and then here I take that difference, okay, and here I have the second derivative. Now, the great thing about this is that it turns out that between two different choices of this delta plus, which they said corresponds to different choice of a Hadamard state, this difference is smooth. So this map is well defined on everything. There is no problem. You don't have to worry about multiplying distribution. So this is an equivalence of star products. So I guess people might be used to working with these spaces. These are concrete realizations of some abstract algebra, which is, well, defined by the isomorphism class of those star products. I want to actually work with that abstract algebra. So let me introduce it. So let A with the star product, I will just denote by star, be the abstract algebra defined by this isomorphism class. Okay, so this is the algebraic setting. This is all I needed from perturbative AQFT. And somehow this packages all this sort of spectral information as well. Some of these objects are going to come back later. So now I want to use it for something. I want to use it to understand these well, objects in functional renormalization group. So there, a key object is the generating function for correlation functions of interacting fields. So I have to tell you how in this formalism I describe interacting fields. This is again for part of the audience a bit standard. So let's see. So here this is setup, and this is interacting fields. Okay, so how are those defined? So first of all, okay, I've seen there were several talks about Feynman propagator coming in. So there's more than one thing called a Feynman propagator. So here I want to define a Feynman-like propagator, but this is very naive definition in a sense. So Feynman propagator so this is defined, well, we take more or less the definition of the two-point function, but change the relative sign between delta retarded and delta advanced. So this is I have delta retarded plus delta advanced plus the symmetric bit. And I use that to define an exponential product as well. So I take f and g, local functionals, and I define the time-ordered product with the same formula. At least that's my first attempt. I haven't tried that before, so I plug this in and hope this works out. Okay. Well, it doesn't actually. So this guy is much more singular than the two-point function. So I'm not going to just get away with it by using wavefront set conditions. That's somewhat unfortunate. So one needs some work. So for this to make sense, I need to extend some distributions. So I need some distributional extensions. So that is actually delivered to me by Epstein-Glaser renormalization. So this is solved by Epstein-Glaser renormalization. Okay. Because my time is finite, I'm not going to explain this in detail. This is a sort of yet another talk. But this is a method for making sense of essentially these products, okay? So I cannot take powers of the Feynman propagator as it comes out of the box because they are too singular. I have to understand them as distributions defined on the smaller space. So, well, simplest example, m squared minus diagonal, and then I need to extend them. So there is some more analysis that needs to be done. So I assume that somebody else has done it for me, and this is already well-defined product for local functionals with this caveat. And then I can use this to define these various objects relevant for functional renormalization group. Going to do some cleaning, so yes. Because I want to define the interacting fields, and for the interacting fields, I want to use something which looks like a Dyson series. So there is, well, if you look at the physics textbook, well, they use path integral, but that's okay. But you can forget about it, just think about the combinatorics. But the object you're constructing for that uses Feynman propagators. So in the first step, you define the S matrix and then use the Dyson series. I'm going to do it right now. But yeah, all would be well if we didn't have to do that. That's true. But if we want to go beyond the free field, then we have to resort to renormalization. Okay. Any more questions? The board is drying. Okay, so let me define something. So, some things. So there is the S matrix. So let V be a local functional, which we think of as interaction. So we are taking perturbative standpoint. So we have the free action I0, and we add to this the interaction term. So the S matrix S of V is defined as the time-ordered exponential. So time-ordered exponential. And here I should have introduced one more object. So here I'm applying the time ordering map, which is also very similar to some things which we had before. Oops. H bar over 2. And again, with the caveat of renormalization. This has to be renormalized. Okay. And this can also be written just as time ordering applying to the usual exponential. Okay, because I think I'm going to get lost in this, I'm going to set h bar equals to 1 here and just work with polynomials. Sorry about that, but these formulae get really complicated very soon. Okay, so this is the S matrix, and let me now tell you what are the interacting fields. So there is a notion of relative S matrix. So SV is now applied to some other observable, and this is S of V minus 1. So now I'm using the star product, SV plus F, and this actually comes now very close to this Dyson series. So this is a generating functional for interacting fields, essentially. So define interacting fields. Okay, so let me call it xi, or capital Chi, I for interacting. So this is SV minus 1 star SV dot. How do I want to do this? Dot x, where let me give it a test function. So xf of chi is an integral of chi with f, okay, and f has to be compactly supported. So this is the formula for the interacting smeared field. So now with that, well, I can try to maybe connect to the usual formulation of, say, textbook QFT. So in textbook QFT, obviously, you would be working in a concrete state, so in a concrete representation of this algebra A. So pick up a state omega, so this is positive normalized functional on A. Okay, so now given a state, we could make things into numbers. So in particular, so this is on general curved spacetimes. In particular, if we look at the vacuum state in Minkowski, so in the vacuum state, omega 0 on Minkowski. Okay. Also here, well, we assume these interaction functionals to be compactly supported, but we should take the adiabatic limit with the support going to infinity. So let me put it like this in the adiabatic limit. Okay, so reduced in the sort of simplest case ever. Then we have the following. So omega 0 of that interacting field. So evaluating this product in the vacuum then factorizes. So this is called the Gelman law formula. So this factorizes, and we get something like that. So this bit is just to make connection with the usual, say, QFT setting, because this doesn't generalize to curve space. So this is just for reference. But if you have, well, seen textbook QFT, then that might look familiar. So that would be, yeah, so typically you would compute the top and the bottom using path integral. So, did I have lambda? Okay, sorry. Okay. Lambda, yeah, lambda is the coupling constant, so I should carry it with me. Yes, thank you. So this is, well, in usual UFT computed using path integrals. Yeah, so that we cannot do. And this is usually the starting point for the FRG analysis. Yes, please. Yeah. The what? Yeah. Global time function. Yeah. Yeah, that's right. So, because yeah, so here you have to take it with a bit of imagination. So this Feynman propagator is what would replace the usual Feynman propagator. So this is literally just defined as I spelled it out here. But yeah, then the time ordering map is given in terms of that Feynman propagator. It kind of slightly loses the notion of time ordering the way you're used to, because obviously we're not assuming to be in a static spacetime, but it has the same sort of algebraic properties. So we keep as much as we can. Yeah, and well, for that reason, we still call it time ordering. But yeah, I mean, would fail to be what? Well, I mean, the Feynman propagator is defined. The what I call time ordering map is defined up to renormalization, but that's always the problem. I mean, the up to renormalization is also the caveat on well, on Minkowski. Somehow the problems of QFT in terms of, you know, singularities are as bad on curved spacetime as there are on Minkowski, meaning they don't get worse. They don't get better either. Okay, so I have very limited time, so maybe let's jump straight to the point. And this is, I think that the last bit maybe is not that long. So first of all, I introduce current. So I smear my field with variable j, which I identify as a current. Okay, and then define the generating function or time-ordered interacting fields. Okay, so this is the definition, but you can check that it actually does what it says on the package. This is with reference to a given state. Okay, so this is the definition. So for a given spacetime, you have to pick a Hadamard state, and then you write that. So then we define W of j through, or as the logarithm essentially. So we want z of j to be or the pointwise, so the standard exponential of I w of j. Okay, so we have w. Then there is another piece of notation, gamma tilde of phi. This is essentially, well, going through the moves in the FRG. Sorry, so here I changed the variables a bit, so I did something like a Legendre transform. So here, pick a field phi and define j. So to explain this notation, j phi as the solution of the derivative at point j equals j phi should give you phi. So this is like doing a Legendre transform. 2 minutes. 4 minutes. Ha! I got double of what I asked for. Exactly 4 minutes. Okay. So that's almost it. So in FRG, now we also introduce a regulator. Okay, so call it QK, and for us, this is just going to be an infrared regulator, if this means something to you. So this will be essentially a mass term with some, again, compactly supported function, I of x squared d mu x. So it's an extra mass term. And the flow parameter is going to be k. So then I can run this whole story again. So I add this to I0. So that gives me ik is I0 plus uk. I reintroduce all these objects, run the same story. Okay, and finally, so everybody gets an index k, and define gamma k of phi as the corresponding tilde 1 minus qk of phi. Cool. Let me just write down these flow equations. Oh, I can do this one at least. So this gamma k is what's going to flow. Not doing this right. Okay. Okay, so the bottom line. So the flow equation this is the dependence of gamma k on k. And here, okay, there is work to be done. It was done in the paper. So let's write the formula. This is the derivative of that's uk of x. And here, let me write the most beautiful formulation, which I'm not going to derive. Okay, and here minus some distribution. Okay, and this is obtained from the Feynman propagator. Okay, cool. So that's essentially it. Let me just summarize in words what actually happened. So this flow equation needs the following data. So we need to specify the spacetime, and you need to specify the Hadamard state where this is happening. And then what we then obtain inside this equation looks like well, a certain quantity which is renormalized using the Hadamard renormalization with appropriate distribution. So in a sense, so from say QFT on curved space-time viewpoint, we understand this object really well as a matter of calculation. But now we actually have an equation which we can think about solving in general, going, say, beyond the usual Minkowski framework. Okay, great. Thank you so much.